I'm glad to attend this conference. My name is Jinxing Cao from School of Chemistry and Chemical Engineering, Nanjing University of Science and Technology. Today, my topic of our speech is the studies of magnesium hydroxyapatite macro nano film for drug sustained release. First, I will introduce the research background. There are 3 pictures on the left. They are typical example of bone defects. Mandibular defects, cumulative fractures of leg, and bone tumors. The repair and reconstruction of bone defect has become the second largest tissue graft in the world, requiring up to 4 million people annually. This is also one of the hottest spots in medical research. Statistically, bone defects are mainly concentrated in joints, vertebrae, and trauma. The concept of bone tissue engineering has been proposed as a method of bone defect repair and reconstruction constantly updated, which puts forward a higher requirement for biomaterial. In recent years, with a decrease in the number of orthopedic surgeries, related surgical failures are also common. All this, failure of internal fixation due to implant-associated infection led to an increase in revision procedures, while 45% of nosocomial infections developed from implant infections. Also, thousands of orthopedic implant infections can be divided into 3 categories: thousands of infection and predisposing factors, colonization and adhesion of bacteria, and bacterial proliferation and biofilm formation. Obviously, the surface of the implant will be the key to solving the problem. For implant infections, the traditional solution is oral or injection antibiotics. However, overuse of antibiotics can lead to the development of superbacteria that cause the implants to fail. Therefore, we proposed a scheme that directly modified the implant surface with antibacterial agents to achieve non-active bacterial solution to infection. Also, we are considering the use of bioactive material for implant surface modification, which can promote bone tissue repair. However, the effect of slow drug release is better than explosive drug release for repairing bone tissue defect. In this study, magnesium and hydroxyapatite were used as raw material for sustained release film. Mag and its alloys are expected to the next generation of orthopedic implants due to their excellent biocompatibility, biodegradability, and mechanical properties. Mag is one of the most vital mineral elements in human bones. 60% to 65% of the total mag in human body, which is found in crystal mineralities of bones and teeth. Furthermore, mag plays an important role in promoting the growth of osteoblasts and the formation of new bone. HA is indispensable in bone transplantation and defective bone repair. It is challenging to break the bioactive films contain mag particles to take full advantage of this characteristic of mag to obtain a film with a porous structure. The equipment in the figure is a powered laser assisted low energy electro beam deposition device for preparation of snow release film. On the right is the experimental process of this study. Figure 41 shows mag-doped HA film repelled by PLD on the substrate titanium surface. After immersing the film in simulated boiling fluid for 7 days, the film surface appeared porous structure. Thus, microporous structure facilitated the diffusion of the drug covered by the mag-HA film to achieve drug-sustained release. Here in ciprofloxacin hydrochloride film, that is a CRP film, as a drug representative is obtained by LEBD to verify the sustained release effect of mag-HA film. In addition, in vitro store compatibility tests showed that mag-HA film had better store compatibility than HA films. In order to further explore the potential value of mag-HA film in the field of drug-sustained release, a full-layer composite film was designed to verify the feasibility of mag-HA film for drug-sustained release. As shown in Figure 44, the first and second layer were CRP film. The second and fourth layer were mag-HA film. Figure 45 shows SEM morphology of 5 composite films. In vitro cell tests demonstrated that CIP mag-HA film was not cytotoxic. We found that biotin possesses excellent store compatibility. In Figure 46, it could be affirmed that CIP film also leads to a decrease in water contact angle of the upper mag-HA film. As shown in Figure 47, the 4-layer composite film has been successfully prepared. Finally, the 4-layer composite film was immersed in PBS for different times, and then the antibacterial performance was tested. The result showed that mag-HA film not only prolonged the CRP release period, but also enhanced the drug release in the middle and later stage. Furthermore, mag-HA film expands the application of mag in the field of also orthopedic and provide a bone to patients who need continuous medication to help repair bone defects. Western blot analysis for confirmed the bioactive of protein film, the protein level of BMP2, BSP, and OPG was significantly increased after 7 days of co-culture with biotin film, especially BMP2. However, the rapid degradation of biotin in vivo limits its application value. Mag-HA film as a promising biological certain release material will play an important role in the implant surface modification. Figure 429 shows FM morphology of different films. It can be observed in figure 429C and E that the surface roughness of the films decreases significantly, which is attributed to the layer by layer degradation of the films in the simulated bonding fluid. Besides, some pores are left on the surface of the films after degradation. Similarly, those pores can be clearly observed in figure 410, which are formed by the explosive degradation of magnesium in the films in contact with simulated body fluid. On the one hand, indicated that magnesium and the bonding were rapidly degraded, and on the other hand, indicated that bonding film had no infrequent effect on the release of magnesium in the magnesium film. Therefore, it can be considered to design a 4-layer composite film composed of magnesium film and bonding film, with bonding as the outermost layer. Figure 4-11 shows SEM image of different film. It can be seen from figure 411A that bonding powder appears as a non-strip with a diameter of 7 to 10 micro. However, figure 4-11B, the morphology of the biotin deposited on the surface of titanium subtracted by LEBD had changed significantly, and the bonding film presented a penta-like structure uniformly covering the surface of titanium substrate. Figure 4-12 shows the HNMR spectrum of biotin powder and biotin film. As a vector, it was found that these peaks all exist in the biotin film without a chemical shift, which also indicated that the bonding film prepared by LEBD technology could protect the biotin structure from degradation. Figure 4-13 shows FTIR spectrum of different film. This also demonstrated that PLD LEBD complete technology can realize the preparation of multi-layer composite films and retain the characteristic functional groups in bonding. As shown in figure 4-14, the composite films has a 4-layer structure. Figure 4-50 shows the procedure of titanium rod implantation in SD rad femur. Titanium rods with 50 millimeter in length and 1 millimeter in diameter was used as the implant. The bilateral hind legs of 6 SD rads were used to prepare the model. The left leg is 14 film group. The right leg is 4-layer composite film group. Figure 4-16 shows the micro-CT image of the red film after 3-week implantation. It can be clearly observed that the number of new bone trabecular around the 4-layer composite film group was greater than that in the bonding film group. To further analyze the osteogenic effect of the 4-layer composite film in the medullary cavity of the rat film. Histological analysis was profound. Figure 4-17 shows the histopathologic views of HE and mushroom stained tissue section taken at the end of the third week. In figure 4-78 and C, the osteogenic rebound of implant loaded with a 4-layer composite film was significantly higher than that of implant loaded with biotin film. Tissue section loaded with 4-layer composite film showed continuous bone structure and intact bone marrow structure throughout the observed area, and the newly formed bone becomes lamellar. Besides, in Figure 4-17B and D, upon the osteoid and webbing bones were formed around the implant loaded with the 4-layer composite film. As bone film was difficult to play a sustainable role in the physiological environment due to rapid degradation. The mag-HA film is in the 4-layer composite film relies the sustained release of drug so as to play a better osteogenic effect. These are highlights in this study. Nevertheless, the number of animal experiment was too small to draw conclusion about the efficacy of the 4-layer composite film in the treatment of bone defect. But I believe that more experiments and longer-term results are needed to confirm the efficacy of the 4-layer composite film. Finally, thanks to the following organization for providing research funds and experiment platform. Thank you very much for your value guidance.